This is problem 4-38. It's on page 199. An insulated piston cylinder device contains 5 liters of saturated liquid water at a constant pressure of 175 kilopascals. Water is stirred by a paddle wheel while a current of 8 amps flows for 45 minutes through a resistor placed in the water. If 1/2 of the liquid is evaporated during this constant pressure process and the paddle wheel work amounts to 400 kilojoules, determine the voltage of the source. Also, show the process on a PV diagram with respect to saturation lines. Okay, that's a mouthful. This one will take us a little bit longer. Here's the system. I'm going to draw it in state 1. There's the piston. We know we've got H2O in the system. Shaft work comes in the amount of 400 kilojoules. The pressure is constant throughout. The pressure in state 1 and state 2 is the same. It's 175 kilopascals. And the electrical work that comes in, we don't know how much it is, but we do know that electrical work comes in. Let me extend these. And we also know that there is some electric potential across this resistor, basically. We know that further a current, usually use a half-headed arrow for current for whatever reason, a current of 8 amps flows for a time of 45 minutes, which by the way is 2,700 seconds. A lot of times I'll just convert what's given to me because I know it's easier to do it then. The initial volume that's given, V1, is 5 liters. Again, I converted that. It's 0.005 cubic meters. I'll frequently do that. I'll just convert liters to cubic meters right off the bat. Saves me time later. And how did this say that it began? Well, it begins, let's see, 5 liters of saturated liquid water. That's state 1. What have they told us about state 1 that we need to write down? How do you write saturated liquid water?
You just write down it's saturated liquid water. You can just write it all.
We could write it this way. Quality equals 0. Right? Now, if half of the mass of the water evaporates, what have they told us about state 2?
6.5.
Exactly. The quality in state 2 is a half, because half of it evaporates. So half of it's in the vapor phase, half of it's in the liquid phase. They gave us the quality directly in this problem, which is really convenient usually. Okay. Anything else that I've missed? I think we've got all of it.
That's given.
Yeah, it's given. I think that's it. Okay, now, before we jump into a bunch of equations, let's think about this and try to see if we can come up with some answers on our own. Let's try to understand what's going on rather than just throw a bunch of math and equations at it and hope it works. Okay? So, if the water evaporates, did the water gain energy or lose energy? It must have gained energy, right? Now, where did energy enter the system? Well, there's some work that came in here that's shaft work. There's also some work that came in that is electrical work. You say, well, isn't that heat that came in? Well, it depends on what system you take. If I take the system to be this system, including that coil, well, then what's crossing the system boundary is work. If I didn't include the coil, what's crossing the system boundary is heat. It doesn't really matter. I'm going to let it be work because all this coil does is convert work to heat, okay? Or convert work to thermal energy. Okay? Now, if we want to quantify the electrical work, we have to do that some way. We have to have some sort of equation to do that. But before we get there, so far we've noted that energy comes in here, energy comes in here, and there's an increase in energy of the water. Is there any place the energy flows out?
Flows out of
Flows out as boundary work. Good job. So you guys are not 220 students anymore. You're good 320 students. You recognize boundary work. This is important. This is very good. Okay. So we've identified 1, 2, 3 energy flows that we need to account for. These are deposits and withdrawals in our bank account. And we've noted that the bank account has increased in value, right? Its energy has gone up. So how would we write that out? Well, the energy balance is pretty simple. Energy in minus energy out equals change in energy of the system. This is the same thing your bank does every day. You deposit some money, you withdraw some money, they'll change the balance in your account. Right? That's all they do. That's all we're doing. Now, there can be multiple deposits and multiple withdrawals. We like multiple deposits, right? We don't like multiple withdrawals. At least if you like for your account balance change to be positive, right? So, in this case, we actually have two deposits and one withdrawal. Okay, so let's quantify that. There's two energy inflows, so really we could write this as a summation if you wanted to. But this equation is more of an idea than it is a strictly correct equation. Okay? So we can add the summation signs. We don't have to. It doesn't matter as long as you understand the concept. So what goes in? Well, electrical work goes in. Also, shaft work goes in. What goes out? Good. Boundary work. Now, how does this system store energy? Does it store energy as heat? Thermal energy. It's not heat. And usually what we talk about is internal energy. Internal energy is the sum of thermal energy and chemical energy. Do you think the chemical energy of the water is going to change any? Going to have any reactions? I don't think so. Okay, so just the thermal energy or the internal energy, which is the sum of those two, is what's going to change. So what delta U.
I guess it depends what the coil is made of.
Yeah, I suppose it could. Suppose it could.
That's a big U, right?
That's a big U because this is all energy. This is not energy per mass yet. We might make it that way in a minute. In fact, we may have to. Well, I don't know. We'll see. No, we don't have to. We've got the initial conditions of pressure and volume. We've got the quality. We should be able to come up with the amount of mass in the system without too much trouble. But let's continue from our high level, just balancing energy. One of the keys to these problems is almost always balancing energy. Okay? Now notice the electrical work is really the unknown quantity, right? Because if we knew the potential, the electric potential in volts across this resistor, or this heating coil, well then we would know the amount of energy that flows in. We could figure that out, okay? But we don't know. So essentially we're going to somehow get it from here. Now we'll take care of the details of how do you put volts with amps with whatever to get electrical energy, but we'll take care of that later. Right now, let's just find out how much electrical energy is required to make this process happen the way they said it happened, right? The way they said that it's gone to half the water evaporating. Okay, so really this is our unknown. So let's put it on one side of the equation. Change in energy of the system minus shaft work plus boundary work. And the reason I've rearranged it this way is because it looks, not because it looks nice, but you can understand it. The electrical energy provides the change in the account balance, provides the energy, it provides the boundary work, it doesn't have to provide the shaft work. The shaft work is helping it a little bit. Does that make sense? So just, that's the little bit that it didn't have to supply to make this happen. All right, now the hard part, well, there's two hard parts to these problems. One is figuring out how many terms you need, where all the energy flows. Students frequently miss things like boundary work and then they don't know how to deal with electrical work. But the other hard part is figuring out, okay, how do I quantify each of these things? How do I put an equation to it, expand it into an equation that I can put numbers into? Okay, so let's see if we can do it term by term. The unknowns on the left, electrical work. How would you expand this change in internal energy term? What would you do with that? You could try to use mCV delta T. Why would that not work? Is there any temperature change? We don't know the temperature, but we could find it out because it's a saturation.
There's a phase change.
There's a phase change, that's right. There's only a phase change, and therefore there can be no temperature change. In fact, we could figure out the temperature from the very beginning. They didn't ask for it, but let's go look it up. So go to the back of your book.
116.4.
116.4, thank you.
I was going to say at the beginning, and then you're like, let's go through anyway. Okay, I'll keep my thumb here.
So that's in degrees Celsius, I assume, correct?
Yes.
Yeah. I didn't do that in my solution, but it's something we could know. And since we evaporate water, the temperature is going to be clamped right there because the pressure is set at 175. Everybody agree with that, 116.4? Okay.
04.
04, okay. the separation there. Okay, well, that was interesting, but still, how are we going to quantify this change? I took you back to the saturated tables for a reason, trying to jog your memory. What else do they have in the saturated table that we may be able to use to solve our problem? They have a UF and UG, right? In fact, wouldn't the internal energy in state 1, this is a little u, just be UF because it's all liquid?
Yes.
What about U2? How would we quantify the average amount of internal energy given that half of the mass is in the vapor phase and half is in the liquid?
Well, we have quality, and we can use that formula. The average of it is minus UF over UFG. So U average minus UF.
I think the one you're looking for is U2 is equal to UF plus X2 UFG, right? Because that would give us the average internal energy in state 2. Now, you'll get the same thing if you do this. Watch this. You can also, in this case, write UF plus UG over 2. Does that make sense? Sure. Half the mass is in the vapor phase, half is in the liquid. So the internal energy is just going to be the average of these two. This is the only time it works because the quality is 50%. I can show you mathematically why it is this way. You have to expand this to UG minus UF, but I'll leave that for you as an exercise just to show. Okay. Anyway, so for our purposes, let's go ahead and calculate the internal energy in state 2, and let's read off the internal energy in state 1. So give me UF.
0.001057.
Did you read off VF or UF?
No.
That sounds like VF.
Yeah, UF 486.82.
486.82 kilojoules per kilogram, right?
Yeah.
Okay. So that's what goes in here for UF. 486.82 kilojoules per kilogram. Then we have to add to that, I'm sorry, it's getting messy. I tell you what, let's do it this way. Let's just continue. Section that off. Okay, so the quality in state 2 is 50%. Do they have a column of UFG? I don't remember. I think they do, don't they? Okay, so what's UFG for that row?
2037.7.
So plug this into your calculator, please, and give me the internal energy in state 2. Now I'm solving this a little differently than what I did on my sheet. On my sheet, I combine the boundary work with the internal energy change. That's all well and good, but I want to show you another way to do it.
Let's see. I got 1505.6.
Yep.
Okay, thank you for verifying that. So there's our internal energy in state 1 and state 2. How do we use it here? Well, it's easy. U2 plus U1. So now we realize we need the mass in order to solve this, right? We've got some other terms to work with still yet. Minus shaft work, may as well write that down because we've got a number for that. That's no problem. But we need to expand the boundary work, so I'll put a dot, dot, dot there for now. And let's figure out how much mass is in the system. How could we do that? Well, don't we know the volume in state 1? And couldn't we say that the specific volume is VF? So isn't the mass in the system, let's see, where shall I put this so it's not too terribly awful? Do you guys understand how we got this? Can I erase this bit and just move the number over here? Is that okay? All right, let's do that. I need just a little bit of space. I don't need that either. 1505.6 kilojoules per kilogram. Now that gives me just a little bit of space down here to work with. Couldn't we do something like this? Mass equals volume in state 1 over the specific volume in state 1? Because the specific volume is cubic meters per kilogram. Here, let's look at that. Cubic meters in the top, cubic meters per kilogram in the denominator. Invert and multiply the dimension or the units, and you'd see you'd be left with kilograms, right? So, by the way, what is the specific volume in state 1? It's just VF. because it's all saturated liquid, right? So while we were back there in the saturation tables, we should have looked up VF. So let me write down 0.005 cubic meters, and now give me that specific volume you're trying to
Point
give me.
001,057.
Cubic meters per kilogram. So now, plug that in your calculators, please. Of course, it's going to be about 5. It's going to be a little less than 5, in fact.
4.73.
4.73. So now we've got the mass in the system. Thank you. 4.73 kilograms. Anyone second that?
Yeah.
So now we've got the mass. That takes care of this piece, and this piece. The shaft work was given. So now let's take care of the boundary work piece. How could we calculate the boundary work?
Well, we have that constant.
It's a constant pressure, so which equation should we use?
We can use,
P V2 minus V1, you got it. So let's expand it to P V2 less V1. The volume in state 1 was given, that's no problem. What's the volume in state 2? How do we get it? Well, what we'll have to do is say, I guess I'll borrow some space here. How do I want to do this?
You can just move the mass.
Yeah, let's do this, but I don't want to erase that. V1 over the, the F1 or V1, it doesn't matter for now. This was 4.73 kilograms. Okay, now, how are we going to get the volume in state 2? Well, how about like this? The volume in state 2 is the mass multiplied by the specific volume in state 2. Let's just transfer our ignorance, right? Well, could we get the specific volume in state 2? Yes. Remember what we did for the internal energy in state 2? We can do the exact same thing for the specific volume in state 2. It would be VF plus X2 VFG. Okay? It's exactly what we did for the internal energy in state 2. Basically, all we're doing here is saying some of it's liquid, some of it's vapor. If we know what percentage is vapor, then we know how much of that we have versus how much of the liquid we have. And that would give us the average property. For some reason, students get all hung up on this. I did too. Don't feel bad if you did. It took me a while. I'm going to be completely honest with you. I probably didn't really understand it until about the second time I taught this course. Okay? So
Said half the mass evaporate from that.
half the mass is in the vapor phase. That's right. So that's where the 50% is going to be right here, X2.
I was thinking just M over 2 times
Right, I understand, and since it's a half, it would work. But when it's not a half, you need this form of the equation. It's more convenient. Now, if you want to figure it out intuitively and say, why is this working? Well, the quality in state 2 multiplied by the specific volume of vapor less the specific volume of liquid. Okay, if we write it this way, notice that we could expand this. Like that, right? So we'd say, whatever percent is in the vapor phase gives us some volume. And we want to assume all of it is in the liquid phase. Oh, but wait a second, not all of it's in the liquid phase. A percentage of it is not in the liquid phase. Does that make sense? So if you think through this, I think it'll make a lot of sense to you. It makes sense why we do this. Okay? But you have to kind of wrap your head around it. It takes a little while to do that. Okay? Anyway, make sure I got that right. Yeah, that's right. So for now, let's go ahead and plug in numbers. I'm going to move up to make sure I'm on the video. So 4.73 kilograms multiplied by VF, which you told me was 0.001 what? 0.057?
Yes.
Okay. Plus 50%. There's the quality, 50%. And how much was VFG?
1.0037.
And these are cubic meters per kilogram, because it's specific volume. So see how the kilograms go away? We'll be left with cubic meters. Okay, so plug into your calculator, please, and let me know what this should be.
Well, that's not VFG, that's just VG.
Close enough, isn't it?
Yeah, I mean,
And then we could do this.
yeah, it's not gonna change it.
Okay, so basically what I just did was I took VG and subtracted off VF, but really it's only gonna change this
Yeah.
decimal place. So now it is VFG. And of course, this is not much anyway. Half of this is still a lot bigger than this, but go ahead and throw it in your calculator and see what you get. How much is the volume in stick
I got 2.38,
2.38?
I believe so.
That's, should be about right. This is about one, this is about a half. So it's gonna be about half of that number. So 2.38 cubic meters.
Yep.
Well, now we've got everything we need. We can plug and chug, so let's do it. Okay, so the mass is 4.73 kilograms. The internal energy in state 2 is right here, 1505.6. Internal energy in state 1, 486.82. Those are kilojoules per kilogram. So we put V2 over here somewhere. That way we've got it by the time we get there and need it. Because I'm going to run out of video space quickly. That's just the first term. We have to subtract off the shaft work, which is 400 kilojoules, and then add the pressure, 175 kilopascals, multiplied by V2, 2.38, less V1, something tiny. Now notice we've got kilograms there and there, so we'll get kilojoules for the first term. This is the bank account change. We've got kilojoules on this term, and a kilopascal times a cubic meter is a kilojoule, so all of the units are consistent. Okay? Now, before we just throw all of this into the calculator, let's take one more step. Calculate each of these terms one by one. This one's already done. I want to compare the relative magnitudes of these terms. Okay? So 4.73 times this difference, this is about 1,000. This is going to end up being about 5,000 or so, minus 400, and then whatever this comes out to be. So 1505.6 less 486.82 times 4.73.
4819.16.
So this is the change in internal energy. That's the amount of money left in the bank account. That's how much the bank account changed. We added 400 kilojoules. In other words, the electrical energy did not have to put this $400 in the bank. Okay? Because the shaft work did it. What about the last term? What about the boundary work? What about the withdrawal that came out? So this is the shaft work. How much is 175 times this difference?
415.63.
Thank you. You see how the shaft work essentially just went out as boundary work? See how they're about the same size? Okay. So how would you like to do that to your bank account every day? Deposit $4,800, withdraw 400, and deposit 400. Well, that's not exactly the way to read this, right? This is the account balance change. This was actually a deposit that the electrical work didn't have to make in order to get the balance to change by that much. But this was an actual withdrawal, even though it has a positive sign here. What we're doing now is just calculating how much rich uncle whoever has to deposit to get this to change, even though somebody else is contributing $400 and we spent $415. Does that make sense? Okay. Now, we're not done. They didn't ask how much was the electrical work. They said, how much is the voltage, right? What's the electric potential? So go ahead and plug all these three in your calculator. You'll get about 4,800 or so. Let's see. In fact, you'll get, I don't know. Just plug it in your calculator. We'll go back up here because we're pretty much done with the energy balance. So just sum those together. What do we get?
4834.79.
I'm sorry, I missed it. 48 what?
4834.79.
Thank you. Okay, so there's the deposit we need from the electrical work. Okay? Now, here's the part you may not be real comfortable with. That's the electrical part. Remember that slide I gave you that had electrical work and electrical power? Okay? I don't remember that real well, personally. I always think through it and figure out what I need. Okay? I know that if I multiply the electric potential by the current, that I will get power. Okay? So, because it's volts times amps gives you watts. Okay? So I start setting it up and just figure it out. So the electrical power would be volts times amps, or potential. Really, the electrical engineers use that symbol for potential, and they always measure it in volts. Okay? It doesn't matter. Let's just use volts times amps to figure out, be used to that. Okay? Now, on the other hand, the relationship between electrical energy and electrical power is the same as any relationship between power and energy, right? So all you have to do is say, if I know the flow rate and how much time it flows, then that is the total amount that's transferred. Does that make sense? So, this is just volts, amps, and then we need the amount of time that flows. Okay? So you can think through these things. Once you understand power and energy, you don't have to remember the details of some of these equations, you just know how they work. Okay? So, let's rearrange this, because what we really want is what's the electric potential. So the electric potential in volts would be equal to the electrical energy transferred over the current in amps over the amount of time. Now, of course, we've got some unit conversions to do here, so let's take care of that part. 4834.79 kilojoules divided by a current of 8 amps. Okay, multiplied by, let's see, where is it, 45 minutes or 2,700 seconds. Okay, what are we going to do with this? You guys aren't used to working with the unit of amps. Well, recognize something. What is a kilojoule per second? It's a kilowatt. That's right. Kilowatt? Kilowatt. Bad jokes. So a kilowatt, so if we've got essentially watts over amps, then we've got volts, except there's this kilo here, so don't we end up with kilovolts, right? So plug this in your calculator, this mess, 4,800 and some odd, divided by 2,700 divided by 8, and we'll calculate from this the electric potential in kilovolts. Okay. So I'll wait till you do that. .223? 0.224. Anyone agree with that, disagree? Okay, we got a second? So basically 224 volts. Okay, when I solved this problem, I got 224 volts, also is 223.8. I went a different way. I combined the energy balance is gone, but I combined the boundary work with the internal energy change, like your author likes to do, because it's a constant pressure process. So I went that way, and I like to solve it on video and for the class a different way, okay, so that you can see both methods. Any questions?
So for that second method, you would use the enthalpy of the system instead of...
Yes, for the second method, what would end up happening is the internal energy and boundary work would be combined into enthalpy. So you use H1 and H2 instead of U1, U2. Then you wouldn't have to mess with P delta V. Okay, anything else?